Morning, ladies and gentlemen, dear colleagues. So it's a pleasure for me to give this talk today. So I thank you, the organizer, for this invitation. So the title of my talk is the recent advances in the understanding of the Gigacycle fatigue resistance of two alloys. First, a cast aluminum alloy and a titanium alloy. So this work is a synthesis of several PhD, which were prepared in cooperation with my colleagues Nicolas Ranc from the laboratory PIM in Paris, and from the laboratory Mathéis in Lyon, Professor Buffière. So I want to thank two PhD students or young doctors now, Alexandre and Louis Hébrard, and another one which contributed a little, that is Arnaud Julie. So as all of you know, probably, according to recent research during the last 25 years, probably there is no infinite fatigue life. And we have to consider for ensuring a very good reliability of structural integrity that cracks may appear even after very, very long life. And recent incident or accidents, you have here two examples. An example with a high-speed train around 30 years ago, and a more recent accident with an Airbus reactor in 2017. And the responsible for such some accident or small incident were internal defects. So in a very high cycle fatigue, the role of defects is very well known in terms of crack initiator or trigger for the crack initiation. In a high cycle fatigue regime, around 1 million or 10 million loading cycles, there is a very famous Kitagawa-Takahashi. Oh, I have a problem with Anyway, on the left, you can see the Kitagawa-Takahashi diagram, which gives you the effect on the fatigue strength at, for instance, 10 to the 7 cycles of the square root area of the defects. And up to a critical size, we can see that there is no significant effect on the fatigue resistance. And when the defect is too large, it decreases drastically the fatigue resistance. But the problem is that such diagram doesn't explain why, when you decrease the stress level, the fatigue crack initiation shifts from the surface to the internal. And up to now, we know that the critical defects are in the material, and it gives a typical pattern like the fish eyes here, but we do not explain why there is this shift from the surface to the core. So the objectives of the different works we have leaded with the PhD students was to answer to the following questions. We would like to do direct observation of internal cracks, initiation and early crack growth in order to try to understand the mechanisms. And we would like to compare the kinetics of the crack at the surface and in the core of the specimen. And the aim is, in fact, to study the effect of the environment on the crack growth under plane strain conditions, because in literature, many authors explain that the criticality of internal defects and surface defects are different because the stress and strain state are different. At the surface, you are in plane stress and plane strain in the material. So in order to reach this goal, I have organized my presentation with the three main parts. First, I will present you the materials, in fact, the materials in the specimens, because they are very correlated together. I will explain why. Then the second part is devoted to the experimental method or methodology and the techniques we have used. And the core of the presentation, of course, is devoted to the results and the analysis, before to see some conclusion and prospects or challenges for the future. So the first material is a cast aluminum alloy with a silicon magnesium, which is very well known. This is A357 in the T6 state. So this is, I could say, a classic aluminum silicium magnesium alloy. This alloy has been produced by the French Research Casting Center in Paris. I emphasize on the fact that this is exactly the same alloy produced also in other research project published by Serrano, Munoz and co-workers approximately 8 years ago. So we were able to take the results of the literature and to compare their results with the surface crack with our results on internal cracks. So our materials has a second dendritic arm spacing around 28 micrometers. This is an important parameter for the fatigue behavior. And we have the typical microstructure with an alpha aluminum matrix and a silicon particles. So these materials were casted in round bars in order to machine inside the bars the specimen. And 2 batches were prepared, in fact 3, but today I'm presenting only 2 of them. So the 2 batches of interest today are the reference batches for the reference fatigue strength of the material with the smallest possible defects we can produce by casting. And the second batch of specimen are specimen with a single big, I could say a big defects in the center of the bar. So we have created an artificial internal defects with a diameter of a little bit less than 1 millimeter, around 700 or 800 micrometers. So these big defects that you can see here, so on the left here, you can see a tomography on a slice of the tomography, and you can see in a specimen with a diameter of 3 millimeters, the internal artificial defects, which is produced by a small piece of salt. And you can see it here reconstructed after tomography in 3D. So the defect is in red, and around there are pink, very small natural defects. So the idea of this central defect is to promote the crack initiation in order to be sure that where we will observe the phenomena exists and not elsewhere. We have also produced some flat specimen for classic crack growth measurement with a classic fatigue testing. I will not present, I present only the results about the other specimen, the other materials, sorry, are specimens in a titanium alloy. So again, this is a titanium alloy which is very well known in literature. This is the TI-64. It has been obtained by hot rolling, and after we have applied an annealed treatment. So this is an alpha-beta classic microstructure. Most of the microstructure is the alpha phase, around 44%, with a grain size which is very smaller compared to the other alloy, around 10 micrometers. So in such alloy, since it is produced by hot rolling, we are not able to introduce artificial defect easily by the manufacturing. So we decided to introduce an artificial defect with a special procedure. It has been prepared and defined by Arnaud Junet. It is published in this paper in Scripta Materialia. So the process is the following. You cut small pieces in a flat titanium sheet, and we produce at the surface of one sheet a sharp notch, a very small sharp notch by a laser femtosecond. And then we polish very precisely the surface of 2 plates, and then we bound the 2 plates by a sparse plasma sintering. So this process is made under vacuum, so it is interesting because in this case, you obtain finally a piece of titanium with a very sharp notch in vacuum in the center of your specimen. And then after assembling these 2 plates, the specimen is machined by turning. Of course, we have obtained precisely the position of the sharp notch by X-ray tomography before the machining, and then we are able to know that the defect is in the center of the specimen. You have here a 3D images of the defects. Its typical dimension is a length of around 200 micrometers, a width of 120, and an opening here of 20 micrometers maximum, typically 15, sometimes 20. And the other set of specimens produced use the same procedure, but the idea is to allow the air of the lab to come into the crack inside the specimen. So we produce by always laser machining, we produce a small canal or a small chimney that allows the air molecules to come into the crack, into the center of the specimen. So we use the same procedure, and finally we obtain the specimen with the central defect and the chimney to allow the air to come into the specimen. So now I'm presenting the experimental method and the techniques. So in order to observe the crack initiation, we will use in situ fatigue experiment with synchrotron. And I'm presenting also the specificity about the specimen geometry. So our needs in order to be able to observe the crack initiation and the early crack growth are the following. So I explained that we want to be focused on internal crack initiation. So we have introduced artificial defects and we test in the very high cycle fatigue regime because we know that in this case, we have the maximum chance to observe internal crack. And to do the test in a realistic conditions because the synchrotron time shift allow you typically a few days, sometimes 2 or 5 days maximum. So we need a quick test. So we do the test at ultrasonic frequency. And to detect the crack initiation during the ultrasonic fatigue testing, it is necessary to use an ultrasonic system that is able to detect automatically the crack initiation. So I will show you on the next slide the principle of the testing machine. So the testing machine needs to be mounted on a synchrotron beamline. So we need a light invisible ultrasonic testing system. And we need also, in order to maximize the chance to observe the small crack, a procedure that was proposed by Professor Nakamura in Power Course. That is to, after testing in ultrasonic, we need to put a small tensile loading in order to open the internal defects or internal cracks. So he has already observed internal cracks in a similar titanium alloy here, but you see that the cracks are very difficult to observe because the contrast between the crack and the microstructure is very small. That's why opening the internal crack is very important. So we have designed the following apparatus that is described with a lot of details in these 2 papers. So now, because of the limit of the time, I present very briefly the system. It is based on a classic ultrasonic testing system. So a classic ultrasonic system is based with a piezoelectric actuator here, the cylinder that is here. And this piezoelectric produces a vibration at 20 kilohertz that is applied here at the top of a horn. This horn amplifies mechanically the vibration, and this vibration is applied at the top of the specimen. So the specimen is here. So this system is mounted on the beamline of the synchrotron. And when we do not load the specimen at 20 kilohertz, we need to be able to do the scan, the X-ray scan, in order to reconstruct the 3D geometry of the material and of the defects. So to do that, we have decided to mount the system on a tube, and the tube is loaded vertically here by an electromechanical system, and the specimen with a special geometry here with a shoulder is put in contact with a load cell in order to apply the quasi-static loading when there is an X-ray. When there is no X-ray, in order to automatically detect the crack, we use a laser vibrometer that is monitoring the vibration of the specimen at the free hand here. And by monitoring with a fast Fourier transform in real time the appearance of second and third harmonics, it means the nonlinearity of the system due to crack initiation, we are able to detect a crack of typically 100 micrometer. So the methodology for testing is the following. At the beginning, when the specimen is a virgin without any cyclic loading, we do tomography. It gives a reference state of the material and of the defects of the microstructure. And this scan is done at a load level corresponding to 80% of the stress level that you want to be applied during the testing procedure. And then step by step, we apply cyclic loading. So a first block is applied up to the detection of the internal crack initiation by the fast Fourier transform analysis of the velocity of the free end of the specimen. And then a tomography scan is done to obtain the image of the cracks. And then we run again a cyclic loading during a number of cycles that has been programmed. Then we observe again the increase of the crack and so on, up to either the breaking of the specimen or up to the end that you decide because, for instance, the stress intensity factor becomes too high. So now I'm presenting the results and the analysis and the discussion of our results. So first, I'm presenting the results about crack initiation, and then we will see the crack growth mechanisms and the Paris diagram. So first, I'm presenting the results in a classic Wöhler diagram. Our results are the symbols in black, and the open symbols correspond to literature data on the same alloy published by Serrano-Munoz. So first, you can see that the results we obtain are in agreement with the results of literature, especially because in a very high cycle fatigue regime, the results have a large scatter. The other point that is important is all the symbols with an arrow corresponds to cracks which are initiated in the specimen, but the specimen are not broken. So it means we know the history of the crack initiation and growth up to this point, up to this slide. For instance, here, up to approximately 2 to the 7 cycles. We obtain this image of the internal defects with the crack. We know the evolution of the crack after different number of cycles, but the specimen is still, the integrity is still good. It is not broken. So today, I'm presenting the results on 2 specimens, the specimen 1111 and the specimen 56. I have not enough time to present all of them. So first, the specimen 119. This one is very interesting because it has a very special response that we observe only 2 times, 2 specimens. So first, on this specimen, we have loaded the specimen at 60 megapascal, and the first crack was detected after approximately 410 to the 7 cycles. And we apply the testing procedure step by step. So it means we apply several number of cycles and we try to observe the crack propagation. But in fact, after 10 to the 9, we observe no crack propagation. The crack was arrested. So since the time is limited at the synchrotron, we decided to increase a little bit and we load again the specimen at 70 megapascal and we continue the procedure. And we didn't observe any crack propagation again. So finally, we decided to increase, and step by step, we increase the stress level. And finally, we obtain only the crack, not propagation, but the appearance, the initiation of a new crack elsewhere in the microstructure, in fact, behind the defects of another crack. And finally, we observe that at 10 to the 8 cycles. So, but it means the specimen history is all these load cycles. So now, if we try to understand why we observe that. So in fact, if I summarize graphically the loaded history of this specimen, it is illustrated here. You have the stress amplitude applied and the number of cycles. For information, you have here the duration of the test at 20 kilohertz to show that in fact the test is realistic in 1 day. So the first crack initiated is here, is in orange. Here, in fact, there were 2 cracks, one here and one here, but these 2 cracks were arrested. And finally, a new crack has initiated after all this loaded history, but here on the back and here around. And these 2 cracks here are not connected. So in fact, we have the global loaded history of this specimen. And this history shows that in gigacycle fatigue, the crack initiation is not always dominating. So it is an important result. Sometimes the cracks are arrested. So you can see here, for instance, after we have broken the specimen in a voluntary manner under quasi-static loading in order to observe the internal defects. And you can see here the defects. The original crack is here, and the second crack in blue is here, and the second crack has initiated here on the left and then propagated. By digital contrast tomography with the synchrotron X-ray, it's also possible to know the microstructure of the specimen. So the microstructure in terms of the grain orientation and the grain dimension has been obtained here before the cyclic loading. So we have labeled given a number of each grain. And in this case, we are able to know the interaction between the cracks and the interaction between the slip systems. So in the next slide, I will try to explain why sometimes the crack is stopped on the grain boundary and why sometimes the crack are stopped in the grain. So if you look at the microstructure and the cracks in this specimen, we obtain at the beginning the following 3D configuration. There are the 3 cracks, A, B, C. And you can see here that the crack A, B, C are all in one grain, number 18. So the question is why only one crack, the number C, was propagating in the neighboring grain, here, number 2, but not the other in the neighboring grain. So to do that, classically, we have computed the Schmidt factor in the different grain and the different slip system. And it's easy to see that the cracks in the grain 18 as propagated according to the highest Schmidt factor, which is the system 4 here, S4 that is illustrated here. That's why the crack C propagated on the grain 25. You obtain the crack C prime because the Schmidt factor is very close to the possible maximum, 0.5. But in fact, around the defects, there are many grains. There is not a unique grains. So we have computed in all the grain and all the slip systems around the defects. In our case, there were 360 slip systems, the Schmidt factor, and we observe, in fact, that around the defects, the distribution of the Schmidt factor is the following, and there are 13 slip systems with the Schmidt factor very close to the possible maximum, very close to 0.5. And there are 33 slip systems with the Schmidt factor higher than 0.44. But nevertheless, we will see why the cracks has the observed configuration. So in fact, in literature, we know that when there is a crack interacting with the microstructure, that the crack is able to tilt and to twist to change its propagating direction. So we have computed in the neighboring grain the 2 different possible configurations. Either the maximum Schmidt factor corresponding to the maximum possibility of slip, and the angle of the twist and slip, and tilt corresponding to the minimum deviation. And we have observed, in fact, that the crack C corresponding to the propagation in the grain 2 propagate through the grain boundary because it corresponds to the maximum Schmidt factor, but not the minimum deviation. Each time you look at the minimum deviation of the tilt and twist angle, you do not obtain a high Schmidt factor. So in fact, it is clear that the crack propagation is governed by the slip activity in the neighboring grain, and the crack doesn't try to minimize the tilt and twist deviation. So this is also an interesting point that we can see here. A detailed observation of the fracture of the specimen after the cyclic loading by fracture by quasi-static loading show us that the crack propagation was parallel to the activated slip systems, but the cracks were stopped in the grain where the crack propagation becomes perpendicular to the active slip system that is in front of the crack. So it is interesting to understand why the cracks can stop. And it shows also that most of the propagation is done in mode 2. That is classic in literature for surface crack also, because we know that the initiation and the early crack propagation is done in shear, so in mode 2. So now, let me focus on the other specimen, the number 56, yes, which was loaded at 75 megapascal. So for this specimen, we have the complete loaded history, and it is very useful in order to reconstruct the crack growth kinetics. So again, we have observed 3 cracks, but this is another specimen. I gave the same name, crack A, B, and C, but the cracks configuration is completely different. So we know here illustrated in false color, the initial crack that was detected by our testing system. So the first crack is in green here. it was detected after 1.85 10⁷ cycles. And then step by step, you have here the increment of number of cycles that was decided to observe step by step the crack propagation. So we have observed the crack initiation on the crack A, and finally this crack was stopped, and we have observed then the propagation of two other cracks, B and C. So in order to reconstruct the kinetics of the cracks, we need to compute, of course, the stress intensity factor and to know the advance of the crack. So the advance of the crack has been given by the 3D analysis by tomography. So after meshing the defects obtained by tomography, we have decided to define the crack increment by the direction perpendicular to the crack front. So perpendicular in a 3 direction because it's a 3-dimensional problem. And we have computed the stress intensity factor range by finite element analysis with the Z-cracked software. We did an elastic computation because we are in a very high cycle fatigue regime. And we have assumed that the crack closure can be taken into account in a very simple manner because, unfortunately, under ultrasonic testing, we are not able to know what is the opening load. So a simple way is to consider that the crack is open as soon as we consider only the tensile part of the fully reverse loading. So it means we have neglected the compressive part of the cyclic loading. And to consider that the crack interact with the microstructure, it means it propagates in a mixed mode. We have computed the range of the equivalent stress intensity factor according to the strain rate energy release rate. The strain energy release rate. So we have obtained the following results plotted in the Paris diagram. So there are many things plotted in this figure, so I will take a few minutes to explain. Our results are in orange. Our results are the internal cracks at 20 kilohertz. These are the orange stars. So first, all these points correspond to the crack advance all around the crack front after different instants of the loading. So when the crack is small, the cracks oscillate between propagating at a low speed and arrested, like a classical small crack at the surface that is interacting with the microstructure. And you can see that when the crack is long enough and loaded corresponding to a range of the stress intensity factor approximately higher than 3 megapascal square root meter, the propagation is a very good agreement with the surface crack data obtained in vacuum. These data are coming from literature obtained by Rotella in 2018. If we compare this crack propagation also with the surface crack in air, we can see that the propagation, when the crack is long enough, are in very good agreement with the surface crack in air at 20 kilohertz. So it means that at 20 kilohertz, probably the effect of the environment has not enough time to be applied, and that's why the surface crack propagate in the same way. And if you compare to a surface crack in air at a low frequency, typically 20 Hertz, this is the data also of literature, we see that there is a very big difference in strain rate, in crack growth rate. So we can keep in mind that the microstructure play a very important role on the crack propagation. The small cracks behave inside the material like a surface crack in vacuum. So probably there is a very big effect of the environment, and we will see that on the second part of the presentation. So to conclude this first part, we can see that in situ synchrotron ultrasonic fatigue tests are very useful to obtain a direct observation of the internal cracks. It shows that the internal cracks initiation do not dominate the total life of the specimen in very high cycle fatigue regime, and the crack may be arrested at the grain boundary. That's why there is a very important role of the slip system of the neighboring grain around the crack. It is also important to keep in mind that microstructure play a very important role because of the mixed mode that is governing the crack propagation, and that the internal small cracks at 20 kilohertz has a propagation like surface crack in vacuum. So now I'm talking about the titanium alloy experiment. So if I show you in a Wöhler diagram the results obtained with the 3 sets of specimens, so I remind you for the titanium alloy, we have the virgin specimen without any defects, a specimen with an internal defect obtained by a femtolaser machining, and another set of specimens with always the defects at the middle of the specimen, but also a chimney in order to bring the air molecules inside the specimen. We obtain the following results. The results in black are results from literature on the same titanium alloy. So first, we can see that our results without the defects, the purple symbol here, are in agreement with the literature. But the most interesting thing is to look at these results. If you compare the specimen loaded more or less at the same loading level, around 310 megapascal, we can see there is a big difference in the fatigue life between the specimen with the internal defects and air inside the crack and the specimen with internal crack without air. And we see that the fatigue life is very, very reduced when you put air inside the specimen. So we try to understand that. So first, I show you here a quick video of the crack initiation and crack propagation obtained by tomography. So this is a projection along the vertical axis of the specimen. So you imagine the specimen is loaded perpendicular to the screen, and you can see the projection of the crack. So you can see its evolution, and on the right and the bottom, you can see the projection by the 2 cutting planes. So you can see here the artificial defects and then the propagation of the crack. So you can see that we can reconstruct step by step the propagation of the crack to build its history. So if you plot the kinetics of this crack in the Paris diagram, you obtain the following diagram. So the blue round point corresponds to our data without air in the crack. And these data are compared, this is the cross, compared with data coming from literature on a similar alloy at 20 kilohertz. So we can see that our data are in very good agreement with the literature data. Then if we look at the same experiments, but with air inside. So this is the equivalent, of course, on another specimen. So you can see here the defects, and you can see the vertical here chimney, and the same here, that is allowed to the air to come inside. And here, only qualitatively, you can see that the crack propagation is very faster. So of course, it depends on how I build the video, but you can see here that the number of cycles coming from 0 here to 3.5 10 to the 5 is very quick. So you can find that on the Paris diagram. This is the red square. So our data are the red square, the specimen with the chimney, compared to the blue round point, the same specimen without air. So you can see that when delta K is small, there is a very big difference in the crack growth rate. And our data are compared with the red cross coming from literature data. So again, we can see that our data are in agreement with the literature for specimens with crack, but with a surface crack. All the cross corresponds to literature data with a surface crack in air. So this diagram shows that an internal crack with air propagates at the same speed for an equivalent delta K than a surface crack in air. It is interesting to compare our results to surface crack in vacuum at the same loading frequencies than our experiments that is 20 kilohertz. According to our knowledge, there is a unique study published by Gitters and co-workers from Michigan University, and I reported their data here. So this experiment corresponds to, again, a titanium alloy, similar to our titanium, but with a surface crack in vacuum. And you can see that in this case, the surface crack here, this is a point surrounded in yellow here, propagates similarly to our internal cracks. And in these studies, they reported also a surface crack at 20 kilohertz, but not in vacuum. This is the cross highlighted in yellow. And when the surface crack is not in yellow, is not in vacuum, sorry, you see that the points are in good agreement with the surface crack of literature and with our data. So now if we have a look on the surface fracture in order to see the mechanisms, a part of the mechanism, as we know in literature for gigacycle fatigue fracture feature, we have observed a black area or a dark area, a bright area, and the fisheye. So first, if we look at the specimen without a chimney, we can classically observe in the black area here, a rough surface and the small facets. This is in agreement with literature observation. You can see the facets here by different workers. And if we want to know what's happened in the facet, why is there this facet, we have cut it by fib the facets and observe it. And we observe that there is a unique grain that has been observed by transmission Fukui diffraction, and we see that there is a unique grain, so probably this grain was broken by a cleavage or quasi-cleavage. If we look just around the facet in the rough area, we have observed by EBSD the microstructure, and we observe nanograins below the granular region. That is also classic, but we observe also, surprisingly, some nanopores. You can see the nanopores here. The scale is very small. So we have both nanograin and nanopores without air. Now, if we look at the specimen with air inside the crack, you can see here the pre-crack and the chimney. Around this pre-crack, there is a dark area, classically in literature, with a very crystallographic zone. And in the bright facet around, we observe very planar area, very frequent and very large compared to the initial facets we have seen in the other configuration. If we zoom on these facets, what we can see striations. So striations because of the presence of air. So like for a surface crack in air. So it is typical in fatigue. We know that the surface crack in vacuum doesn't exhibit striation, but the surface crack in air exhibits striation. And here we observe that for an internal crack. And the last slide about the mechanism is the following. We have cutted here the defects and observed by EBSD the corresponding section. And we have observed below the fracture pattern that you can see here, from the chimney to the notch and then to the bright area. We have not observed any difference in the black and bright region, and we didn't observe nanograins or nanopore. No modification because we are in air. So for the titanium alloy as a conclusion, what we can say that there is a big difference between an internal crack propagating without air or with the presence of air. The fatigue life is very, very different. So there is a detrimental effect of air on the crack propagation. As soon as there is presence of air molecules, the speed is very high compared to vacuum. And when we are in vacuum, we can observe nanograins and nano-hole, but not when there is air. When there is air, we observe only striation. So this means there is a crucial role of the environment for the internal crack propagation, but there is no effect of the plane stress or the plane strain state. This is the contrary of many assumptions proposed in literature to explain the difference of internal and surface crack initiation. And last but not least, our observations are in agreement with the cold welding hypothesis proposed by Oguma and co-workers, because we see that as soon as we introduce air molecules inside the crack, there is no refinement of the microstructure. So probably the layer of oxidation, of oxide, is a barrier for the cold welding process. As a general conclusion, this is my last slide. We can say that in situ very high cycle fatigue experiments are very useful in order to understand the mechanisms of internal cracks. There is a big interaction of the crack propagation inside the specimen with the microstructure, and there is not always a domination of the initiation process, but the crack propagation may dominate. The internal cracks behave like a surface crack in vacuum, and there is a key role, as I said, of the environment. For me, the challenge for the future are the following. It should be interesting to redo the same thing, but with a positive loading ratio. But to do that, we need to find money, as you know, it's difficult. And it's necessary to better understand the environment effect, because in fact, the oxidation is a little bit difficult up to now to be modeled. And I think the most important is to be able to model by a micromechanical model considering the oxidation effect, the internal crack initiation and propagation. Thank you for your attention.